Special transformations, reciprocal graphs. This is actually a topic that you first studied at the very end of grade 11. And so parts of it are going to be a review, and parts of it are going to connect to things that we've done this year, which make it a little bit new. The idea that's a review is if you graph 1 over any function, what is it going to look like? The only thing that happens to that function is that your y values change to 1 over y. And even though that's a simple and small thing, because that's the whole lesson, y values change to 1 over y, a lot of crazy things happen. These were your like sad clown face, or I don't know, you did volcano. Sometimes you gave different names to these graphs because you did 1 over a bunch of parabolas and you did 1 over a bunch of lines. The difference in grade 12 is we can do 1 over any equation we've graphed so far. 1 over a square root graph. 1 over sine. 1 over x cubed with all the transformations. So we're going to re-look at what happens with the 1 over a function graph and how are we going to do that. So to start off with, what I have here in these notes is steps for graphing this. The bold part is the step. The non-bold part is kind of an explanation of why that step happens. So our very first step is we're going to graph f of x, whatever the function is on the bottom, we're going to graph that first. Then on a separate graph, we are going to make vertical asymptotes wherever we have x-intercepts. Now if you think about that, what's the y-coordinate on any x-intercept? 0. And the rule for a 1 over f of x graph, the simple rule, is change all of your y-coordinates to 1 over y. So if you had an x-coordinate of 3, 0, and you changed it to 3, 1 over 0, we have a problem. Because 1 over 0 is not allowed. You have a non-permissible value. And in all of these graphs, because we've learned in chapter 2 that non-permissible values sometimes are asymptotes and sometimes are holes. But for all of the reciprocal graphs, they will always be vertical asymptotes. So our x-intercepts become non-permissible values, and we'll get vertical asymptotes. We will also get horizontal asymptotes. And in these graphs, your horizontal asymptotes will always be at y equals 0. The reason and the way that you know that you're going to have a horizontal asymptote at y equals 0 is if your original graph, either the y values go up forever, get very, very big positive numbers, or they go down forever. So like a parabola that opens down, the y values would go down forever, and so the reciprocal graph will have an asymptote at y equals 0. Now the reason that happens is because those arrows to say that your graph goes up forever mean that your y values get very, very big. So here I have a point. 10,000. What happens when you do 1 over that value? You get 1 over 10,000. And that gets really close to 0. After you've done your asymptotes, the next thing we look at is points. We're going to look at certain points on our graph that we know. We're also going to look at certain points that don't change. For example, if you had the point 3, 1 on your graph, and you do 1 over 1, what happens? Nothing. It stays the same. So some points where the y value is 1 or the y value is -1, those points don't change. They're called invariant points. But you can also look at other points on your graph. Some important other points, if your graph has a maximum or a minimum. So if you had a maximum at 3, 6, the reciprocal of that point will be 3, 1 over 6. So steps 4 and 5 basically say, take a bunch of points that you know on your original graph and change the y value to 1 over y. And then finally, you'll be able to graph everything towards the asymptotes. So showing the asymptotic behavior of your graph going towards the asymptotes. You'll have points in each section, and it will be clear which way your graph needs to go. So on this paper that I just handed out, what I've done is I have shown each of the steps one at a time. Now, if you were doing this on a final exam, you wouldn't do it this way. So we're also going to do it in class as if you were doing this on an exam. The first step that you are always going to do is draw your original function that's on the bottom. So when we're graphing 1 over x squared minus 4, you're going to graph x squared minus 4. That's right here. So I'm going to label some points that I know on that graph. I've got 0, negative 4, negative 2, 0, and 2, 0 already labeled on your graph. What are some other points you could plug in that you know? What happens when you plug in 1? You get 1, negative 3. What happens when you, well, 2's plugged in, what happens when you plug in 3? So again, you can go to your equation, actually plug in 3 for x. You're going to get 5. And by symmetry over here, you're also going to get negative 3, 5. So we can get a number of points on our original graph. Then right beside it, I'm going to go through all these steps that are done one at a time here. I'm going to do it right beside it just as one graph, because that's how you would do it on an exam or on a test. So on our graph to the side, we would start with our asymptotes. We're going to have vertical asymptotes wherever we have x-intercepts. So on this graph, can you see that you have x-intercepts at negative 2 and at 2? For your horizontal asymptote at y equals 0, does our graph either go up forever or go down forever? Yeah, it goes up forever. So we will have an asymptote here at y equals 0. Once you're done your asymptotes, then you can go to your points. Take the points that you have. What's going to happen to 0, negative 4? 0, 1 over negative 4. What's going to happen to 1, negative 3? 1 over negative 3. Well, we can't do 2, 0 because that would have been an asymptote. But if we do 3, 5, we'll get 3, 1 over 5. Same thing over here. I'll get negative 3, 1 over 5. So I think it was step 4 in our steps that said, find the values where y is equal to 1 and negative 1, the points that don't change. But sometimes you don't need to do that because those points, like, apparently it's equal to 1 about here, right? But I don't know the x-coordinate of that point. So I could, if I wanted to, estimate where that point is on my graph, or I don't need to put it. It's not a necessity that you have that point. But now that you have points in each of those sections, sometimes you're going to have enough information to draw your graph. Like in our middle section. Can you see that it's going to go down towards the asymptotes? In our section to the right, the one where I have 2 points, it's going to look like this, and the same thing is going to happen over there. And what did you call this graph? That was a sad clown face, right? I think we're the only school that calls them that, but it's kind of fun. Okay. Second example. We have the graph of 1 over x squared plus 1. Well, that's our x squared graph, our parabola, shifted up 1. Drawn right here. Off right beside it, I'm going to go through all the steps, starting with asymptotes. And so I sort of remember things as 3 steps. Draw your original function, step 1. Step 2, all your asymptotes, vertical and horizontal. Step 3, some points and graph. And it's really not that much to remember. So step 1 is our original function, already done for us. Step 2, asymptotes. Will we have any vertical asymptotes? No, because we have no x-intercepts. Will we have a horizontal asymptote? Yes, our graph does go up forever, so we will have an asymptote at y equals 0. Points. Well, I've got 1 point labeled on here. Let's label a couple more. What happens when you plug in 1? You'll get 1, 2, 2, 5. By symmetry, we'll also have -1, 2, -2, 5. So, what happens to those points? What happens to -2, 5? -2, 1 over 5. What happens to -1, 2? -1, 1 over 2. 0, 1. 1 over 1 stays 0, 1. And then you'll get 1, 1 over 2 and 2, 1 over 5. This is enough points for us to draw the asymptotic behavior. What did you call this one? Speed bump. Yeah. Example 3. Finally, we have one that's different. So the first 2 examples were ones you did in grade 11 with parabolas. But now we can put any graph on the bottom and follow these same rules. So if we have the square root of x plus 4, we start by graphing the square root of x plus 4. That's a square root graph moved 4 to the left. Right beside it, do we have any x-intercepts? Yes. We have an x-intercept at -4, so that becomes a vertical asymptote at -4. Does your square root graph keep getting larger and larger and go up forever? Yes, it does. So you will also have a horizontal asymptote at y equals 0. Step 1, graph the original function, done. Step 2, do your asymptotes, done. Step 3, do a bunch of points and draw your graph. So, what's going to happen to -3, 1? It's going to stay the same. 0, 2. 0, 1/2. If you wanted to do another point on this one, what's the next nice point with integral values on that graph? Five, 3. Right? Because what are nice numbers you can take square roots of? Square root of square root of 4 is 2. Square root of 9 is 3. We already did square root of 4 when we plugged in 0. So the next one would be square root of 9. In order to get square root of 9, x has to be 5. And where's that point going to go? 5, 1 over 3. And so we can draw the graph with the asymptotic behavior. Notice that on our original graph, there is nothing less than -4. There's going to be no graph less than -4 on here. Any good names for that graph? Big ramp, okay. Water slide. Came up with this morning, boomerang. Anyways. And sometimes the graph is something that you can draw with transformations like the first 3. You could draw the bottom graph. Sometimes the graph will be given to you, like this last one. So they give you the graph and say, can you graph the reciprocal? So again, we'll do it right beside. Step 1 is done because they gave us the graph. Step 2, do we have any x-intercepts? Yes, quite a few of them. Oops. We got one at 1, one at 2, and one at 5. So one at -1, one at 2, and one at 5. Step 2, does our graph go up forever or down forever? On the left, it stops. Is there an arrowhead on the right? Yes. There is an arrowhead on the right, so we will have an asymptote at y equals 0. Now we take our points. One of the things I wanted you to see in this example was when you have a horizontal line in your original equation, from -5, -1 to -2, -1, it becomes a horizontal line in your reciprocal line graph. Now, this one happened to stay exactly the same because the values were at 1. But if it went from -5, -4 to -2, -4 as a straight line, then it would become a straight line all at -1/4. Other points that we have 0, 1. Can you see that that point is going to stay the same? We have 4, -1. That point is going to stay the same. And we have 6, 1. That point is going to stay the same. Now, sometimes you're going to get a sense that, and you're going to say to yourself, I don't know if I have enough. I'm not quite sure. Should my graph go up or should my graph go down? So if that's the case, right here we got a straight line. Should it go up towards the asymptote or down towards the asymptote? Okay, some of you might say, I know that it's going to go down because I don't want to cross that asymptote at y equals 0. That's a good logic there. But you can also take a point. For example, if I make my y value -0.5, what's the reciprocal of -0.5? -2. And then you go, oh, it does have to go down because of that. And if I take all the values that are -0.5 all the way across and say they all have to be -2, it's going to help you with those sections. And the same thing, you could do +0.5 and figure out this part has to go up. And that part looks like that. Notice, and even check your notes, there's no arrowhead on the end of this part. Okay? Sometimes you get into the habit, maybe you're really good at it, you feel really good. I don't ever forget arrowheads anymore because I don't want to lose the half mark. So whenever I finish a graph, arrowhead everything. For these ones, be careful. Because if this part of the graph didn't have an arrowhead originally, this part has to stop there as well. On this side, the arrow continues, so it's okay that our graph continues on the right.